Hi, thanks. Thanks so much for joining this webinar. And my name is Igor, and I'm the CTO and co-founder of zkEVM. And today I want to talk about zk rollups and zkEVM in general. So let me present my screen first. Yes, and then I'll start. Play it from the start. Let's hope it works. Can you confirm? Can you check that you see my screen? Okay, so now you see my screen. So let's wait for maybe like 20 more seconds. In the meantime, I'll prepare to draw on the screen. Okay, so yeah. So let's get started then. So as I said, my name is Igor, and I'm the CTO and co-founder of zkEVM. I came from an engineering background. I've been working in the blockchain space for quite a few years. A lot of them were spent as a core dev on Ethereum itself in the Aragon team, and also some kind of a core researcher on the protocol side. Right now, I'm also a little bit working on the Gnosis chain and also on kind of the protocol side and things like this, and also on the Polygon zkEVM, which is basically the topic of today's presentation. Before all that, I've been in the traditional Web2 kind of building browsers at Opera and doing some fintech and some other things. So what I want to talk today is basically I will first talk a little bit about rollups and validiums in general, what the layer 2s are. Then we'll go a little bit into details about zkEVM in particular, and a lot of them works in a similar way, but I'll focus more on the Polygon because that's what I am more familiar with. So there's some technical details there, and also we'll do a little bit of a recap and some parts of the private rollups thesis that I was talking about a few times before. So let's start with the rollups and Validium. It all started that at some point we figured out that on Ethereum it became kind of the victim of its own success, right? So the ambition of Ethereum always was to be at first the world computer. Right now is more like a settlement layer for the world, but the global scale was there always, right? And then very quickly we achieved, like I think it was even before 2016, it was very clear that with the architecture of Ethereum that was largely inspired by Bitcoin, you cannot achieve the world scale because you very quickly saturate the network. It becomes very expensive and very slow. So at that point, there were some projects basically to scale Ethereum somehow. And the first project was it was called Serenity back then. I think it was in 2016. It was then called Ethereum 2.0, but it was basically the idea that we can split the chain into multiple shards, like the database that needs to be scaled. You kind of split it into multiple chunks, and each chunk might have its own execution environment. It might have its own smart contracts. It might have its own completely like a different set of applications on them. Some of them could be like even without application, purely for transferring a value. And then we have this kind of a beacon chain in purple in the middle that's orchestrates and kind of makes everything come together, like make sure that you can interop between those chains. And this was a very, very ambitious plan. But it also was really, really difficult to implement. So at some point in time, and also it was, by the way, one big part of this one was that Ethereum becomes proof of stake instead. So it was like multiple parts of sharding for scalability and also proof of stake for creating blocks in Ethereum too. And then at some point, the decision was made. I think Vitalik wrote a post, like the rollup specific roadmap for scalability or something like this, that we will split proof of stake from scalability, and we do the merge for proof of stake, right? And then scalability we kind of outsource to third parties, and there was this concept of rollups when basically, or layer two, that basically instead of trying to shard the blockchain itself, you keep the base layer as is, and then you run kind of a little blockchains with special properties on top of this. And these blockchains will be cheaper than the layer one, they will be more scalable, and in the end you run applications on those layers. And maybe lately you can also add like a layer 3 on top of one of the layer 2s here and run applications there even more cheap. And the main kind of idea, there were different types of layer 2s suggested, like maybe somebody remembers the word like plasma at some point in time. Then it's like there were some side chains, but the biggest one in the rollup specific roadmap was the word rollup. And the rollups is what we want to talk about. So let's start with the basics and what is a rollup. So if we talk like really precisely in like a technical term, rollup is like a blockchain or something that runs on top of the base layer, like on top of the layer one, and it has two properties. It has to share kind of two things with the base layer. One is data availability. That means that even if rollup shuts down completely, you should still be able to recover its state from Ethereum. That's basically was the idea of the on-chain data availability. And the second part was on-chain proofs. And these proofs are different kind of proofs. I will talk a little bit later about them. But basically, remember that there are two things. You need data availability, you need proofs. The problem with that is that the data availability is quite expensive, because that means that you need to essentially publish a lot of information into the into the layer one, into Ethereum. And that's why there was this another concept that you probably don't hear that often, because everybody likes to call themselves a rollup, but that was a validium. And validium means that it only has on-chain proofs, but data availability actually relies on the layer 2 itself. So we see here in the schemas that in the rollup schema you have Ethereum here, you have Ethereum as a layer 1, right? And then you have a special smart contract of a rollup. And then this rollup publishes, there are two arrows. One is for data availability and another one is for proofs here. If it's a validium, then Ethereum is still here, right? But then it's only the proofs that have been published, but no data availability whatsoever. And then just for fun, there's also a layer 3. Basically, there's a certain layer 2. We don't know what it is. This Ethereum is here right now. And then layer 3 is on top of another layer 2 and also does proofs and data availability. And of course, you heard that there are two types of rollups right now on the market. One is called the optimistic rollups and another is zero knowledge rollups. Let's start with optimistic rollups. And the difference between those rollups is basically the type of proof that they publish. So for optimistic rollups, there is this concept of fraud proofs. Essentially, optimistic rollups are optimistic, and all the state transitions they take for granted until you are challenged, right? So if you are sending your money into one of the optimistic rollups and execute there basically, and then you think that somebody did something weird with your money there, then you can challenge the rollup and provide a fraud proof. And then let's say you can essentially erase one of the transactions or something from optimistic rollups, or replace it with something else, because if it's an invalid transaction, you can always challenge it. But by default, everything goes. And there are two biggest ones are Arbitrum and Optimism. Both of them are, by the way, supported in Gateway FMS, public RPCs. They are the biggest ones. The big issue to some extent with those two is that Optimism definitely doesn't have these fraud proofs implemented yet, even though it's a couple of years old already. Arbitrum, I think it's moved further a little bit with that, but still it's not really great in terms of the fraud proofs. So the second type of the rollup, which I think is more future-proof and more interesting, is zk rollups. And unlike optimistic rollups, here you don't have to trust anything, right? So every transaction that happens on zero-knowledge rollups has to have a proof, and this is a proof of correctness. So that means that you can actually do this transaction. So for instance, if Alice has 1 Ethereum and then Bob has 0 Ethereum, and Alice sends half of Ethereum to Bob. So let's say we have Alice with 1 and Bob with 0 here, and then it sends 0.5. Then there should be a proof that after this it leads to Alice 0.5 and Bob 0.5, right? So that and you need to kind of have a proof. There is this interesting word zk here, which means zero knowledge, which is usually a privacy technique, but in zk rollups it's not used for privacy. Actually, what you want from these proofs is that it's kind of a side effect of what zk proofs are. They can prove generic computation in a very compact form. So that means that there is nothing to do with privacy in zk rollups. It's all about being able to prove smart contract execution, or to prove a transaction and all the rules of state transitions, so-called state transitions in the blockchain, to prove all of them in a very compact form, so the proof is not enormous. And then you see that there are a couple of companies that are working on this tech. One of them is Starkware, another is Matter Labs and Polygon, and then there are multiple rollups that are already live, and starting from Starkware, StarkX and StarkNet. Then Matter Labs has zkSync Lite and zkSync Era. Polygon has zkEVM and some other ones as well, and also Scroll is one more like I would say, I don't know, like even more like decentralized, or like more made by a decentralized organization than the others. And then if we're talking about the data availability, in particular in rollups, there are two approaches to them. One approach is to publish the transaction themselves to the layer 1. So for instance, if I'm setting like transaction 1, then transaction 2, then transaction 3. In this case, in the first approach, everything goes to L1, all of them. Maybe they are compressed somehow, but they all go into layer 1. Another approach is to publish the outputs of these transactions. Means that we have the state at first, right? We have the state 1 or something like this. And then after applying this transaction, we have state 2, and then there is some kind of a delta applied in here. So we take this delta and store this delta to layer 1. Both have its own pros and cons. Like for the inputs to layer 1, it's much easier to recover the state from layer 1. In theory, like if you have many transactions to the same account or same smart contracts, the approach of publishing outputs will produce more compact, basically more compact data availability calls, so less gas on L1. But it also depends if your rollup is a general purpose rollup, and then you basically send. There's a lot of transactions going on between different parties. Then of course it's still a big chunk of data you need to publish. And then Validiums in particular also have a couple of approaches there. First of all, you might hear this local data availability, and that basically means that, trust me, I'm the operator. I will not go anywhere because there is no proofs. You cannot really take state from anywhere apart from the Validium operator. And the second is data availability committee, and those are basically usually some third parties involved. Maybe there's some data Validium operator stores this data, but then some external parties involved, and then you kind of have to trust the committee. In both cases, there's nothing to do with layer one, and those are technically not rollups. So if you hear the word like a rollup with local data availability, that's not a rollup. That's Validium, and that's the important part. So to recap the rollup theory, to be able to call yourself a rollup, you need to have two components. You need to have data availability on layer one and proofs of layer one. Both of them are necessary. If you have Validium, then you don't need to have on L1 data availability. They are cheaper than rollups to run, less gas used, but they are also less secure in case of if something goes wrong with the rollup itself. And then there are two types of rollups. Optimistics have fraud proofs, means you trust them, but you should be able to challenge if something you don't like happens. And then zk rollups has to prove each transition. So as soon as the proof is verified, you can on the layer one, you can have trust that the state transition was correct. Now let's specifically focus on zkEVM and what's different about those types of rollup. So historically, they've been like, since zk technology is difficult and to prove some generic code is really, really difficult, you can kind of figure out the generations of rollups there. So the first generation of zk rollups were StarkX and zk Sync Lite. They were very specific operations in them. So basically, you cannot run smart contracts on them. You can only run the operations that were kind of hard-coded or predefined by the rollup operator. In zk Sync Lite, it was like transferring ERC20 tokens. In StarkX, also like transferring ERC20 tokens and some NFT operation. And that's it. You cannot do you cannot do anything you want there. So the second generation is I call them Starknet and zk Sync Era the second generation because they can take your Solidity code and then convert it through some kind of operations into their own virtual machines. But this virtual machine is not a EVM. It's not a Ethereum virtual machine. So that means they have a special tools here. In terms of Starknet, there is some tools written by Nethermind. I forgot the name, but whatever. There is a transpiler from Solidity into their language Cairo that then compiles in their own virtual machine. In terms of zk Sync Era, they use LLVM to compile Solidity directly into their own virtual machine, and these virtual machines are made so they are very efficient to prove, but they have nothing to do with compatibility with Ethereum. And the third generation, or like the current kind of zkEVM equivalence, is what Polygon did with Hermes with the current zkEVM, is when you compile Solidity into EVM, and then basically the rollup has its own EVM implementation where each opcode of EVM, let's say it has some kind of a push 0 or I don't know, some other opcodes like SHA, I think, or things like this. All these opcodes, they have proofs to them. So it's a much more difficult task, and the proofs are to some extent bigger in this case because EVM was never designed to be proved by basically zk proofs, because when it was designed, there were no zk proofs or no idea to scaling in terms of zk proofs. But what's cool about this approach is that you can still use your normal Solidity compiler, you can still use your normal Solidity debuggers, you can basically use all the developer tools you are used to for both sending, debugging, decoding transactions, decoding smart contracts and stuff like this. You can still use them in this approach. Whereas this approach kind of requires its own tooling, ideally, to work well, or some special adaptation. So the zkEVM like rollup, when it's deployed, it looks roughly like that. Again, the green parts here are the parts of the rollups, and the pink ones are some extra stuff, and then the purple ones just generic infrastructure that, let's say, we run for zkEVM via gateway run. So basically, as you see, there is like a sequencer, aggregator, and prover. So what sequencer does is it takes transactions from the outside and then puts them in a particular order. What's important to know about the rollups, that most of the rollups, including Polygon zkEVM, they don't really have a notion of blocks. So the rollup has just a list of transactions, one after another. And even though you see on like Polygon scan that it has some kind of a notion of blocks, those are more or less artificial. So the sequencer goal is to put this transaction in this particular order. Then what the aggregator does, it combines them together into batches for cheaper proofs. Then the prover, of course, what it does is it's basically generates those proofs that's needed. And then the zk node here, it exposes the RPC, which is the important part, right? That's how you essentially talk to a blockchain. That's what gateways, let's say, zkEVM RPCs expose. And there is, of course, the state DB. Basically, that's the current state and the history of state that are stored in a certain database. And then there's also a synchronizer, which is a little bit different part, because synchronizer, in case of zkEVM, if you start from scratch, like you start a new zk node with all this machinery, what it will do, it first will talk to Ethereum and try to sync as much from Ethereum, because all the proven transactions are already on Ethereum. So it first stores the proven, it syncs the proven transactions from Ethereum, and then switches into currently the centralized sequencer of the zkEVM at Polygon, and just synchronize all the latest transactions that were not yet proven. And then there is one more component to any kind of rollup. It's a bridge. In case of Polygon, it's called LX12Y bridge. I will have a separate slide in terms of how it works. It's a pretty interesting technology, but that's basically the basic parts of what's Polygon zkEVM consists of. I think like the other zk rollups, they are roughly the same parts. There are still sequencer, there's some kind of aggregators and stuff like that. And they also can synchronize from layer 1 if they have data availability there. So now for the transaction lifecycle, what does happen when you basically, whenever you are sending the transaction into the rollup, basically you first send it, and then it's getting stored on the sequencer, and then sequencer puts it in a certain order after a certain transaction. After that, again, the transactions are getting batched, and the batched is basically to make sure that your proofs and data availability costs are smaller, because then you prove a batch instead of approving each transaction, and instead of sending each transaction on the layer 1, because if you send each transaction onto layer 1, not batching them, it will be like a nonsense story when one transaction on layer 2 equals one transaction on layer 1. Then what's the point of scalability in there? So at this point in the red zone, basically your transactions are only stored on the rollup operator, so they don't have any data availability from layer 1. So at this point, you might call them non-final, so something could happen to them. But then the next step is when the transactions are getting sent into the data availability, into the smart contracts on the layer 1. And at that point, you cannot reorg this transaction away. So you cannot really, and then even if the rollup disappears, you can still recover the state in here. And that happens in case of Polygon zkEVM. It happens either every 10 minutes or when the batch is full. Usually the batch is full much quicker than 10 minutes. So, but at worst, 10 minutes after you send the transaction, it's getting sent to the data availability. After that, once an hour-ish right now, I think, on the the proof are getting generated. That means like a big beefy machine. It runs those transactions and generate proofs for each of them, and then compacts this proof together with kind of a recursive schemas of zero knowledge proofs. And then after the proof is generated, it's getting sent to the layer 1, where the smart contract on the layer 1 verifies the correctness of this proof. Again, this proof is made in a certain way that it's relatively hard to make it. It requires quite a lot of computational power, but it's very simple to check this proof. That means that even a smart contract on Ethereum can actually validate if the proof is true or not. So, and at that point, not only you have like a guaranteed data availability, but you also have a proof on the layer 1 that your transaction was executed correctly. So the next thing is what's interesting. I know I told a little bit on this slide about how transactions are non-final in the first part, and then they become final at some point. And this finality period is something relatively new to at least Ethereum, because at first, basically, there is this thing in the blockchains called the reorgs, right? When you put your transaction as get included into block, there is a non-zero chance of this block, at least in Bitcoin, for instance, to be reorganized. Another block will take its place, and your transaction will not be included there. So it will be kind of a reorged away. So in Bitcoin, we figured out that, okay, if your block is on the tip of the chain, there is a chance of reorgs. When it's like another one is on top of them, the chance of reorg is much smaller. If another one on top of that, it's even smaller, even smaller, even smaller, even smaller. And then we figured out that, okay, 12 blocks on top of our block. So let's say it's, if our block is here, we have like, sorry, it's the other way around. If our block is here, and then it has like 12 blocks on top of that, it's basically the chances of reorganizations are basically zero. So that means that, okay, this is, we call it, the transactions are kind of final, even though there is a theoretical chance of reorg away. It's like purely theoretical. And Ethereum worked like that for a while, and then you see in your wallets, right, even right now, the things that, okay, this transaction have this many confirmations, this transaction have this many confirmations, and you kind of, as a user, has to figure out, okay, is that enough for me to trust or not? So when the beacon chain was introduced and the proof of stake was introduced, we had this special algorithm called Casper Friendly Finality Gadget, FFG, that was implementing in-protocol finality. That means that as soon as this algorithm figures out that this transaction or this block is final, by protocol definition, you cannot reorganize it. It just will be it's going to be against the rules of the protocol, so it cannot happen even theoretically. And in Beacon Chain, it happens every 2 epochs, basically. And then it's 14 minutes ish before it gets finalized. Of course, it's like some caveats on this as well, but that's the important part. And then we see that in the rollups, there are also kind of a finality period as well, and we can define it pretty. There's like 2 finality period if you want. We can define it pretty strict. So the first finality period comes when things get sent to the L1 for data availability. As soon as they are sent to L1 for data availability, then they cannot be reorged away from the rollup. That means that in kind of in the sense of finality of the L1, we are already final as soon as our transaction is sent to the layer 1 for data availability, and that means basically every 10 minutes at most. But then we have another guarantee which happens after that, which is when the proof is getting checked. If proof is getting checked here, then we also have another guarantee that it's not only final, but it's also proven. So we don't have to really execute this transaction anymore. We can take the target state if we want. So that's a little bit about the finality. Now the big component of every rollup is a bridge, because otherwise the bridge is the way on how we transfer data between the blockchains, or let's say between layers 1 and layers 2, right? And Polygon has this thing called LX to LY bridge, and it's a pretty cool concept because it's not a single bridge, it's kind of a network of bridges in particular. So it starts with like a smart contract on Ethereum mainnet, and a smart contract on the target chain, let's say zkEVM mainnet, and also some in protocol things between them. Basically, in case of zkEVM mainnet and Ethereum mainnet and other zkEVM based things, it's actually uses the, as a part of the state of the zkEVM, there is the state of a bridge as well. So then it means that when we sending zk proof of a state change or state transition of zkEVM, we also sending a proof of bridge changes onto the layer 1. And that means that since the smart contract here, it both validates, it has access to the bridge, like the rollup contract has access to the bridge contract on Ethereum mainnet. It can actually validate changes on the bridge side as well. That makes it very, very safe to transfer things as soon as the proof is sent. But what's also cool about this, that it's not only checks the state of one EVM, it actually has a tree of states of different potential chains. So you can actually validate state of all of these chains as well. So if you run multiple private rollups or app chains on top of Ethereum, you can reuse the same smart contract for them, and that means that they all will be proven by zk proofs. And moreover, that gives a little bit of a side effect, that then you can not only transfer data between layer 2 and layer 1, but you also can transfer between different layer 2s in a way that you want, and they still will be proven by a certain zk proof on the layer 1. All these transitions, of course, they won't be as quick as between layer 1 and layer 2, but still they will be very, very safe on the other hand. So that's very important, because then each private rollup, let's say, that you might deploy based on Polygon zkEVM, it actually adds to this kind of a system of bridges and makes it even more powerful. Then, of course, the rollups right now are relatively centralized. They're usually, as zkEVM, for instance, is being run, the sequencer is being run by Polygon itself. And but a lot of people want them to be decentralized. But the question is right now, why do we need decentralization at all? And that's the important. And decentralization, I would say that it's not a goal in and of itself. The goal of the blockchain technology is to get rid of trusted third parties, right? And when you have centralization of something, let's say your layer 1 is centralized, that means you have a trusted third party, the people who runs the blockchain, right? And this kind of removes the whole idea of the blockchain in the first place. But basically, decentralization is neat if we kind of can put it in categories. First, to produce liveness of data. That means that no party can basically destroy the data. No single party can destroy the data single-handedly. And then the second is giving agency to the users. So that means that regardless of what's opinion of, I don't know, Infura about my transaction on Ethereum is, or opinion of Gateway for that reason, you can still include your transaction without having to consult those entities. And I would argue here that for zk rollups, agency and liveness are they're partially provided by being able to produce the proofs and data availability things. So basically, if you have data availability, then you already can recover the state, right, from the layer 1. So it doesn't really matter what the operator of the layer 2 thinks. about maybe they went bankrupt, they shut down or something, you can still recover this data relatively easily. And then the agency can be done by this kind of proofs, because there is a notion of so-called forced transactions in zkEVM, when you can send a transaction to layer 1 instead of a layer 2, and then this transaction has to be executed on the layer 2 within a certain time frame. And if it didn't, then you can run your own infrastructure and include it yourself. So it's of course not ideal scenario, but at least it gives a partial agency even in a purely centralized setting. But there is a big caveat here, that in this case the base layer needs to be actually decentralized, right? I wrote a little bit about it here, because if your base layer, let's say if you're not using Ethereum but using your private app chain or something as a base layer, then I mean you are controlling anything anywhere. So that means that you don't have your users don't have anywhere to escape to. That means that layers 2 can only be they will be partially, they give partially less agency than the base layer. But that means that the base layer, like let's say if you use Ethereum, you have quite a lot of like neutrality and agency, because you have a lot of options there. If you use Gnosis chain, that's as well. It has a lot of validators around the globe, a lot of blockchain infrastructure operators and stuff like that. That means that layers 2 built on those, they can kind of get a little bit of this neutrality, gets a little bit of this agency, and use it for itself, even if the layer 2 is centralized. So that means I would say that what I'm saying is like actually it's very important, and it's true mostly for zk rollups. So I would say that zk rollups has in general less need for decentralization than optimistic rollups. But like if you're using like if it's an open rollup, like let's say Polygon zkEVM mainnet, and not a private rollup, then decentralization is still very important, because it's kind of a public good, and you need to, I mean, the slightly less agency than Ethereum is probably not enough, and you cannot really just borrow it forever. So for the main installations like Optimism, Arbitrum, I don't know, zkSync Era, and Polygon zkEVM, you still want them to be decentralized as well. But for the private rollups, you might get away with them being centralized anyway. And that's where the app chain thesis that I've been talking about a little bit before coming in, that you can use actually private installation of, let's say, zkEVM rollups to build app chains on credibly neutral and decentralized networks like Ethereum or Gnosis. And then you get the properties of an app chain, because app chains are very useful when blockchain meets kind of a real world, when you need compliance, when you need certain performance, or maybe you need some unique game mechanics, or maybe you just need to run things for cheap. And then with the zk proofs and forced transactions, you still give your user agency, even though it's a privately run rollup by a centralized entity. Your users still have power, like unlike some banks that are getting, like, let's say, closed and your money is gone until you have insurance. Here you can actually withdraw your money if you want to. And that's one of the things that we are investigating at Gateway, like how to do them better. So we already like running some private rollups, but we are working on making the provisioning of zk rollups much easier, maybe in a couple of clicks or something, when you can get some rollup and some extra tooling like immediately done. And yeah, I think that's about it. That's what I wanted to say. Again, about the gateway a little bit. On public gateway FM, you can get a lot of public RPCs and free RPCs if you want. They are based out of private data center around the globe, not really tied to any cloud provider or anything. And there's quite a few companies already using us. So yeah, feel free to use that. And if you have any questions or anything, you can get my contact details here. And yeah, that was it. Thanks so much for for coming to my presentation here.